It's going to be about what we call morphological quenching, but which is simply the fact that gas disks are more stable against star formation when they are embedded in early type galaxies, and I'm going to show you what numerical and observational evidences we have for that. And first, let me mention my collaborators. So on the theory part, these are Frédéric Bourneau, Avishai Dekel, and Romain Tessier. And on the observation part, this is the Atlas 3D team, and mainly Alison Crocker, who did a lot of work on that topic. So why do we care about the stability of gas in early type galaxies? Well, that's because there is gas and star formation in early type galaxies. And if you were there for Tim's talk on Wednesday, you heard all about it, so this is just a really short version of Tim's talk, but basically Atlas 3D has found that 22% of local early type galaxies have some CO. And the masses of CO can be quite important, from 7 to up to 10 to the 9, so masses of CO in these galaxies. And what is also important is that the CO is not sort of fluffy, large-scale component. It is mostly in really nice disks that are in the center of the galaxy at small radii. In a few cases it is disturbed, and there's also quite a lot of bars and rings of CO in these galaxies. So there is a dynamically cold component of molecular gas in these early type galaxies. And another interesting observation is that in the color magnitude diagram here, the big red points that you can see are Atlas 3D galaxies, color-coded, well, not color-coded, but with a size depending on the mass of CO in these galaxies, mass of H2, sorry. And you see that surely some galaxies with molecular gas are here in the blue cloud, but there's also a lot of red sequence galaxies here with a lot of CO. Even like this one is extremely red and has a lot of CO. And as Tim also showed on Wednesday, these galaxies have a low specific star formation rate and a low star formation efficiency. So the question is, what's going on with this gas? In early type galaxies, what's the state of CO, and how does star formation proceed in early type galaxies? And a reason to expect something different to happen in star formation in early type galaxies can be understood with a very simple stability analysis based on the very simple tumor parameter. So in this sort of classical analysis, the stability of gas results in a competition between a lot of different processes, but mainly the self-gravity within the gas disk, the velocity dispersion or turbulence that stabilizes the disk against the collapse, and the shear, which comes from the differential rotation in the disk. So all of that together gives you the tumor parameter. So this is the tumor parameter for a thin rotating gas disk, so just there by itself. And if this tumor parameter is greater than 1, the gas disk is stable. However, in the universe and in galaxies, gas disks don't live by themselves without a galaxy around, right? And when the gas disk is embedded in a stellar disk, you have to modify your tumor parameter to take into account the effect of stars on the stability. And a simple way to do that is this very simple formula where you have an effective total tumor parameter, which is the sum of the tumor parameter for the gas and the one for the stars. And what this means is that if you have a gas disk that, say, would be with a tumor parameter of 2 if it were by itself, right? So very stable gas disk, tumor parameter of 2. And you put it in a stellar disk that also has a tumor parameter of 2, so say also very stable stellar disk. For this sort of component with 2 intrinsically stable gas disks, the total component, the total tumor parameter is actually 1, right? So 1 over 2 plus 1 over 2 equals 1. So if you take this stable gas disk and you put it in a stellar disk, it becomes unstable. So stars contribute to the instability of the gas disks. Now what is going on is that if you put your gas in an elliptical galaxy, it becomes more stable for 2 reasons. First of all, the potential well is steeper at the center of elliptical galaxies, which means that the shear is greater and this kappa parameter is greater, and so the tumor parameter is intrinsically higher in the regions where you have a lot of shear. But also, as I was telling you, the stars in a disk have an effect to destabilize the gas. Right? So if the stars are not in a disk, but they are in an elliptical component, basically they don't contribute at all to the gas stability. The self-gravity is reduced and the gas disk is more stable. And that means that we expect gas disks in elliptical galaxies to have much higher tumor parameters than gas disks in spiral galaxies. And if you think that stability is related to star formation, then this means that we would expect orbital galaxies to have lower star formation efficiencies than spiral galaxies. And this is indeed what we found and what we call morphological quenching. And so this is a plot that I'll show you again in 2 minutes for simulations where we found, this is just a clinical diagram, so star formation rate versus gas density. In blue are these galaxies, in red are elliptical galaxies, and indeed we find that the gas in elliptical galaxies produces stars less efficiently than spiral galaxies at the same gas column density. So how did we find that result? Well, that's something we found in a Zoom cosmological simulation, where at some point in the simulation we ended up to a state where we have these big elliptical galaxies with 10 to the 11 solar masses of stellar mass. It has created a lot of gas, so the gas has settled here into this gas disk, which you see in purple colors. There's 6 × 10⁹ solar masses of gas in the disk, and the color is quite red. The B-V color is 0.75. So here, in more detail, is the history of the simulation. So before that elliptical was formed, there was a phase of many mergers that formed the elliptical galaxy, and this is what you see here. So in red, the gas fraction, in blue, the star formation rate. So this here, what you see, is a phase where the elliptical galaxy assembled, lots of gas, lots of star formation, starburst. So you get to that point at this stage here. So at this stage here, you have formed your elliptical galaxy. Gas accretion continues, and the gas disk here grows with time. You see the gas fraction increases a lot, up to 10%. However, the star formation rate in that gas disk, so what you see blue, goes down and just stays very low at about 1 solar mass per year, right? In spite of the increasing gas fraction. And when you look at the B-V color, see that during the starburst, the galaxy was quite blue with a B-V of 0.3. And as soon as that is over, the color reddens steadily, and say from the start of the quenching phase, in about 1 gigayear, it gets to this red color. And so here's again the corresponding Schmidt-Kennicott diagram for that same galaxy. So this is exactly what I have already showed you. We find that for this simulation, when the galaxy is elliptical, the star formation efficiency is always, well not always, not in this case here, but tends to be lower than when the galaxy is a spiral. So, this was all very exciting. The one comment that you could make on this is that this was a resolution of only 150 parsecs, which is really good, but maybe not enough to fully resolve the structure of the ISM and the stability of the disk and the properties of the turbulence, which would be a very fair comment. And so we decided to test morphological quenching in some very controlled situation with very high resolution simulation. So the next step was then to use the adaptive mesh refinement code Ramses to run some simulations of isolated, idealized galaxies. And what we did is we took one elliptical galaxy, one spiral galaxy, we put the same gas disk in both, and we see what happens and how that gas disk evolves in the elliptical galaxy and in the spiral galaxy. And because we have just this one idealized galaxy, and because we're using AMR, it means we can go to 5 parsec maximum resolution, so resolve the structure of the interstellar medium. And this is what we get. So this is the structure of a gas disk in the elliptical galaxy. This is the structure of a gas disk in the spiral galaxy. So what you see is that in the spiral galaxy, the gas disk has fragmented in lots of clumps. The clumps have interacting. They've moved to the center of the galaxy. In the elliptical galaxy, the gas disk has remained very smooth. You don't see spiral structure. You see a lot of, well, maybe tiny, tiny little arms there, but there's no high density feature. It's just smooth and stable. And the star formation rate in the spiral galaxy is 2.5 solar masses per year versus 0.1 here in the elliptical galaxy.
So just to check, it was the same mass and the same extent
Yes.
in kiloparsecs, just in a different potential essentially.
So this is a spiral with a Budge-List ratio of 0.1, and this is a purely spherical elliptical galaxy.
Did your scale height of the stellar disk, how did that compare with the scale height of the gas disk?
It was, oh gosh, the scale height of a stellar disk, I can't remember, but probably 200-300 parsecs. I can't remember the scale height, but it was larger than the scale height of a gas disk for sure.
Okay, yeah, because your Q parameter argument only holds if the stellar disk is small compared to
Indeed.
the gas disk, but observed molecular disks can be locally much smaller than the stellar disk.
And you can make corrections to your thermal parameter if you have a thick disk also, so the stability criterion becomes a bit different if you have a thick disk. So the analysis I gave on the thermal parameter is the very basic ideal case, but you can correct that for thick disks and more complicated components. I guess I talked about the thermal parameter just to give an intuition of what could happen, but independently of that, we see this happening in simulations. We can talk about thermal parameter for thick disks if you want, if that's your question.
Yeah, also in the simulations that's relevant if you need to have the gas to allow it to get cold enough for the gases to be thin.
Yep. Indeed. So, what else? Oh yeah. So here, I am showing the gas density probability distribution functions for both galaxies. So both galaxies start with this initial PDF, right, where gas only goes to 100 atoms per cubic centimeter. In the elliptical galaxy, it becomes this PDF. In the spiral galaxy, it becomes this one. So in the spiral galaxy, we reach densities higher than 10 to the 5 atoms per cubic centimeter. When in the elliptical galaxy, we don't go up to, we go, to a maximum of about 1,000. So that explains why star formation, is so much more efficient in the spiral galaxies, because we have all this really high density gas here, but just doesn't happen in the elliptical galaxy.
But magnetic fields in the Milky Way prevent hydrogen from becoming too compressed, right? The H1 clouds are primarily magnetically supported, not thermal gas pressure supported. So they don't form densities of 10 to the 5, they get to densities of 10 or 30.
But this would be molecular gas, not.
Well, still, do you have magnetic fields in your simulation?
Oh, we don't. There's no magnetic field, so it's pure hydro turbulence.
That actually, I think, is important, at least in the Milky Way, for cool gas.
What are the typical densities in the spiral simulation in the gas disk?
What do you call typical density?
At the peak and then where it's lower.
You mean in a...
Oh, there it is. So, yeah. Okay, yeah. In solar mass per square parsec.
Okay, if you just wait 2 slides, I've got a chemical calculation where you can see the actual solar masses per square parsecs instead of these values. Okay. So just a brief mention that we also tried putting a lot of gas in the elliptical galaxy, and in that case we find that even in the elliptical galaxy, the gas disk fragments, and we cannot keep any arbitrary large amount of gas stable in an elliptical galaxy.
But this is a gas fraction of 5%, and the simulation you showed before, which wasn't the idealized one, had a gas fraction of 10%
Yep.
when the disk was stabilized.
Because in that case, the gas disk has a radius of 2 kiloparsecs only. It's because we wanted to mimic Atlas 3D galaxies that have CO radii of a few kiloparsecs. So what matters actually is the surface density of the gas, right? In that case, you have 10 to the 9 solar masses of gas in a radius of 2 kiloparsecs, where in the other cosmological case, the radius was maybe 10 kiloparsecs. So this is the Kennicutt relation. So in blue are the two simulated spiral galaxies, and in red the two elliptical galaxies. So this is the one with the low surface density, where the gas is stable. This is the one with a high surface density, where the gas is more unstable. So does that answer your question, Sharon, about the densities?
Yeah, there's a typical form of
Yep, yep. Yeah, it would be, if we would observe it, it would be molecular law. Okay, so what we also did is a similar exercise that we've observed on galaxies. So that's work that was done by Alison Crocker and the Atlas 3D team. So she took 8 local early-type galaxies for which she had CO maps, so resolved observations, because that's the best way to build your Schmidt-Kennicutt relation. We also had H1 mass and star formation rate maps, for which she used non-stellar 8 micron emission. And in the same way that she analyzed these 8 early-type galaxies, she also analyzed 12 spirals with all the same tools and the same tracers. And this is what we got. So in blue, the data for these 12 local spirals, and in red are the points for the local early-type galaxies from Atlas 3D. And as you can see, again, in all these early-type galaxies, the star formation efficiency is lower than in the spiral galaxies. And at fixed gas density, the star formation rate is lower in the early-type galaxies by a factor of about 2. And Tim has shown you on Wednesday a similar plot where the star formation rate was coming from Calyx and Y is 22 micron, and it was basically very similar. And what is also nice is that a similar thing has been seen completely independently by the cold gas survey. So this was led by Amélie Saint-Onge. So here she shows some star formation rate versus molecular gas for these cold gas galaxies. And the color code of the points is the stellar surface density, which they argue is a proxy for how concentrated the galaxy is, and also if it's an early type or late type. So the red points are early type galaxies and the blue ones are late type galaxies. And
I hate to ask about XCO.
Actually, so they argue.
If you're talking about it later,
No,
then.
I'm not. Amelie argues that over the mass range, the metallicity is not varying so much, and so we're not in a regime where XCO is making a huge difference in.
But there is a stellar density, stellar metallicity relation.
Yeah, but they argue that the metallicity range probed by across this mass range is not changing XCO that much.
It's not
All right.
just the metallicity, it's the photon field.
well,
Maybe actually put this
Also,
up for you.
potentially,
Yeah,
yes,
yeah.
that's definitely still, I think.
yeah, no, it's surely open for comments. But yeah, just to finish on Amélie's result, well, what she finds is that the early type galaxies indeed also have a lower star formations than the late type galaxies. So that was a nice confirmation of our results. So just to conclude, morphological quenching is the very simple idea that if you put a gas disk in an early type galaxy, it is going to be more stable than the same gas disk in a spiral galaxy. And we have both theoretical and observational evidence that the star formation could be 2 to 5 times less efficient in early type galaxies, and we find that this is enough to redden the galaxy. Some caveats here are that orbital galaxies cannot, have any large amount of gas that you want and still be red. There's an upper limit to how much gas you can keep stable. And you can also think that if you have this orbital galaxy with a really nice thin CO disk that doesn't form stars, but a minor merger comes in or some external perturbation comes in, it might be enough to destabilize the gas disk and trigger star formation again. Right? So it might be different for galaxies with multiple interactions. And just to conclude, this idea of morphological quenching could, I want to be very careful there, it could be in part, why we see quenching and bulges being related in observations, and Eric has done a lot of work on this. But I don't think there's any, really proof of that yet. It could be a link, but that's it. And if we just really want to prove that quenching is occurring in these galaxies, we need resolved molecular maps to actually see that there's a lot of molecular gas but not much star formation. And in general, molecular quenching is just, I think, makes life easier for other quenching mechanisms, right? You don't need to totally shut down your gas accretion. You don't need to totally shut down your cooling. You can still have a little bit of gas in these galaxies and still keep them red. And because everyone had their own little rant, this week this is my own very short. We do not make predictions for how much gas there should be in orbital galaxies. I'm not saying that, all orbital galaxies have gas. I'm saying they can. And I guess Silvia Fabello used an argument that she said, we don't find a lot of H1 in orbital galaxies, so morphological quenching doesn't work, but that's not what we said, right? We do not make predictions for gas content. We say there can be some, but that's it. Thank you.
Questions? Let's go from the back. Phil?
So, it'll be annoying to get the comment and a question. The comment is just, and I think you were getting at this with your last point, I think it's important on this to be very careful about the language, because I think a lot of people would not, based on the terms we've been using, a lot of people wouldn't call this quenching.
For instance?
Because you haven't, so a lot of people would say what's quenched the galaxies here is gas exhaustion, right? You've cut off the gas supply. And if you systematically, if I just rerun a simulation where I force the Kennebec relation to be 2 or even 5 times systematically lower than the observations, I don't suddenly produce quenched galaxies. I mean, there's plenty of cosmological simulations that have low KS laws. The problem is you have an overcooling problem, and as you acknowledge, you can only support a very, very small amount of gas in these ellipticals, 10 to the 9 solar masses of gas, which is, it's useful to know that you can support that, but the point is you have to do something to prevent that much gas from getting into your ellipticals, cosmologically. And that's, I think, what a lot of people would call quenching, right? So it's a matter of semantics, but I think it is important because people have misinterpreted your argument.
Well, I don't want to say that, this by itself can explain the red sequence. And I don't think I've ever said that or written
I
that.
don't think you have, but I think calling it morphological quenching, for example, has implied to many people that that's what you are saying.
It was an implicit statement that this is shutting off star formation.
Well, if you look,
Morphological damping.
Yeah.
I don't know, because that's
It's a
what
modulation of the star formation.
that's what we saw in 2009, right? But we had this elliptical galaxy with 6 times 10 to the 9 sort of stellar masses of gas, and that was a reasonable gas fraction, and we saw it become red. And
So I would argue, for example, in that simulation, you exhausted the gas supply. So you turned most of I remember you say in the paper that essentially the halo gas reservoir is exhausted for some time, and then the star formation rate does run away at late times in that simulation.
at late time
cooling flow.
no. At late time, the star formation comes back higher again because there's a merger.
Oh, so
There's a major merger at t equal 11 gigayears there. So that's a merger. That's
so
not.
the point is, as soon as you perturb it or bring in new gas,
Oh, yeah.
it's not.
Well, along the same lines, I was wondering to what degree star formation rates that you find balance the mass inflow rates. In other words, what degree has the system really observationally reached equilibrium, where mass loss rate from stars is balanced by star formation rate in this.
Mm.
And if you looked at that, because that may indicate indeed that you've reached this sort of low steady state of slowly declining star formation.
So this is the only case we have in a cosmological simulation that I've looked at. So we don't have any statistics, I guess, in general.
But your observed set has that data that you can compare with your simulation, right?
Yes. Yeah.
Yeah, there's, so if you have a steady accretion and a lower star formation rate, then you should be building up gas, molecular or otherwise, faster, and these early type galaxies should contain more gas than spirals, not less. But in fact,
yeah.
it has taken a considerable effort to find molecular gas in these galaxies, whereas the first time you looked at spiral galaxies with millimeter wave telescopes, you detected the CO. So these have a 30th of the mass median value, 30th of the mass of molecular gas.
You missed a rant.
I'm not saying yes.
No,
I'm not saying,
heard
but
that,
you
but I
know.
also see that line up there, gas fraction increasing with time.
Yeah, in that case, yes. But this is not, you know.
You know, doesn't putting A and B together mean C, and if you say ignore C?
No. I'm really saying that, you know, there are other mechanisms that shut down gas cooling in early time galaxies for sure. And this is not a message I want to send. I don't want to say we don't need whatever of this other thing that, you know, helps galaxies stay red. But maybe it means that, I don't know, AGN jets don't need to be so efficient as to completely, you know, make cooling go to zero. You can have still a little bit of cooling and still remain red. But I'm not saying that, you know, all of this is not happening. Surely it must happen because we cannot sustain a huge amount of gas in the galaxies and we don't see them anyway. So I hope I wasn't misleading because that's not really what I want to.
A very short quiz.
I don't think you are misleading, and I think this is actually quite very nice and must play a role. The question I had, so as you said, as the surface density builds up, at some point it's going to be too much. And in those simulations, it seemed to be too much already at 10 solar mass per square parsec from your plot, but the observations were up to 1,000 solar mass per square parsec, where it's still low efficiency.
Yeah.
So can you explain that?
X.
Sorry?
XCO.
Yeah, I don't know. I guess we would need to, you know, explore the parameter space a little bit more than these two simulated galaxies if we wanted to really have a feeling for how things are working. What I can say is, so there's one galaxy which is called NGC 524, which has quite a lot of CO, and that we tried to simulate. We tried to have a stereo distribution that matched NGC 524 and a CO disk that matched what we observed, and so on. And we find similar star formation rates in the simulated 524 and in the real 524.
All right.
So,
Thank
yeah,
you. Very
thank
good.
you.